Hello. Right, so let's talk a little bit about equilibrium. So the concept is that we are looking at rigid bodies. And I've said here, if my mouse, I've said here that the body's not moving. I mean, strictly speaking, yes, the body could be moving with constant velocity. We're saying that it's not changing its sense of motion, so there's no sense of acceleration happening there. Go back. Gone ahead by mistake. Right, so that's understood. So what we're saying is that force equals ma. So that when we sum up the forces, they're going to equal 0. So my a is going to equal 0, so I'm not going to have any acceleration. Force is a vector. So let's say that we're just working in two planes, in one plane, so we're going to work in an x direction and a y direction. So I need to have my forces in the x direction, if I add them all up, to equal 0. And then I need to have my forces in the y direction, add them all up, so equal 0. We're working in a plane, so what else could the body could be doing? Well, it could be rotating or turning, so let's put a stop to that. And what we're going to do for that is we're going to sum up any rotational forces. These are the things that come in the form of moments, and we will make sure that when we sum up the moments at a particular point, that they equal 0. So when we've achieved those three things for objects which we're to be dealing with in this module, just objects that are moving in a 2D plane, then we've achieved a state of equilibrium. Now, to find equilibrium, we will probably have to have our body probably attached to something, certainly resting on something. Sort of mechanical engineering type problems we'll be looking at, so we'll probably have some sort of body sitting on what we're going to call reaction points, or call them reactions. And what this means is that any forces that our body will exert, let's say from gravity, a gravity field force, that the reactions, when they come into contact with those forces, they must counterbalance it so that the body's not moving. For beams, we can consider them to be structures, and other structures we're going to look at, such as bridges or anything else like that. So the other thing is we need to be aware of what's called a free body diagram. So FBD. So that's a diagram where we've essentially taken the configuration, the illustration, maybe even the engineering drawings of the problem that we're looking at, and just done another physicsy drawing which will probably have dimensions. Ideally it would be to scale, but it doesn't have to be. It certainly should sort of indicate the scale, but most importantly it will have the external forces on it. So coming up with this diagram is a crucial step in for you to being able to solve a lot of your engineering problems that we're going to be looking at. The reactions need to be put on your free body diagrams. So let's say if you've got a hinge or if you've got something resting on the floor, you've got to decide how's that best modeled, and you're probably going to have to model it as a reaction. You can't over specify how many reactions that you're going to have. Then the problem becomes mathematically impossible to solve. So how we're going to model the reactions is something that's quite important for what you need to consider in a free body diagram. The reactions themselves are usually unknown, so we need to work them out typically. Whereas the external forces that we're going to apply to the body, how much it weighs, or maybe someone standing on the bridge. So those sort of things we will know what we need to apply. So if we took a classic case, let's say we've got a beam, and we've got this beam on these two supports here. So that's my diagram. So then I need to interpret that as some sort of free body diagram. So what kind of free body diagram might I have? Well, maybe I am interested in a little person standing on my bridge and them exerting, what would be a person? Let's get on to maybe 100 newtons? No, 1,000 newtons. If you're 930, so 1,000 is a bit too much, but okay, about 1,000 newtons there, and we're going to have a reaction point here. So I draw that as an arrow. Don't know if I can back up now. And then we're going to have a reaction point here. Okay, so here we're maybe label this as location A, location B, location C. For this problem, because we've said that forces can go, we need to sum up the forces in the x direction and the y direction. Notice that I don't actually have any forces in the x direction. So here we've got to kind of like fix the problem. So we've got nothing to determine whether there is a force going in the left-right direction. And what we'll do is we'll pick on A. And what we do is we say at A we'll have a reaction force that's going vertically, as we would expect. Oh, it doesn't like that. But we'll also have a reaction force that's going, I don't know if it's my little Wii Fit thing. We'll have a reaction force going in this direction. So I'm going to write that up as I'm going to have a reaction RA, and that would be a y direction, and a reaction as RAX. Okay, I won't go into the maths now, but you could say, well, okay, so we're going to fix this point here, so let's fix this point here. Well, in actual fact, the maths would not work if I did that as a I'd be over-determining my framework. So I'm only going to put one point where it's fixed, and the other point I'm going to let it float. So I'm going to let this beam, in principle, expand out in this x direction. Okay, so I'm not constraining it. Okay, so that is my free body diagram. I'll write this up, that's a reaction, so RC, and because we're dealing in both x and y components, I'll label it as RCY like that. Okay, so that would be one kind of free body diagram that you could conceive of. What else? Let's do something else, and let's consider maybe a very simple framework. So some sort of almost like a roof type thing there. So if I wanted to model a roof there, I would again have to fix a particular corner there, and I could have reactions going from the corner. I could call this point A, so that would be RAX, RAY, and I'm going to model this roof as if it's got all the weight coming from the top down like that, down like that. Don't know how much a roof would weigh. Let's go for 20 kilonewtons. And we would need to then support the other timber to stop the roof collapsing, so we'd have our RBY located there and my C location there. So that's another example of a free body diagram. So these are examples of free body diagrams. Okay. So on our configurations, on our illustrations of the sort of problem that we're going to look at, we see things like this. So maybe this is like a ladder, and it's on a smooth surface. So if this ladder is in contact with a smooth surface, not a very sensible thing to do, so you put your ladder on some kind of slippy surface, or maybe ice. That means that if there's any sideways force, that ladder will suddenly just skid away. So there's only one force that can exist. So we're saying that there's no friction here. And so to convert this illustration here, what we do, we would convert this on our diagram with an upwards arrow, and we'd probably not call it force, we'd probably call it R. So that would be the then reaction. Oh, it's really not good. It doesn't like drawing on PowerPoint, sorry. So we'd have an R Y like that. Okay. What else? Well, okay, so that's we've still got, well, let's ignore it. We've still got a smooth surface, but if we've got some friction there, then that means that there could be some sideways force. So we would have to replace this bit of diagram with some with a reaction force going in the x direction there, and a reaction force going in the y direction here. These ones here are symbols that we would typically see on configurations that really represent this thing here. Okay, so we might see symbols of something that looks like a ball, where we've got a rod being allowed to move left to right, or here we've got a kind of crazy hinge where we've got this sort of fixed hinge where this beam is again allowed to move left to right, and it's on these little coasters which let it move left to right. So again, we've got no reaction forces that can occur in the horizontal sense, so all we have is a reaction force going in the y direction. Other sort of shapes that you can have, this one we don't deal with as far as I can recall, and that's where we got a kind of cantilever type thing, where you've got a bit of beam embedded into some fixed surface, and you've also got a bending moment at the moment. So let's not worry about that one, because that's a tricky one. The other case is where we've got a hinge, and we're normally going to draw a hinge like a kind of semicircle. This is really difficult to draw on, sorry. With a big pin joint in the middle there. And so what does that mean? Well, that means that that we've got this pin like this, okay, and this pin is then trying to move around like that, and actually I need to make myself bigger here. Yeah, here we go. So we got a pin. So imagine that's my hook, and then got this pin, and it's trying to push in various directions. So it's always trying to push, but this hook is fixed. It's not letting it push around. So that means that we have got forces that can be pushing either left to right or up and down. So that's why we need then, for this particular case, that we need to have a reaction force both going in the x direction and a reaction force going in the y direction. Where am I? Okay, so let's draw my configuration. So, do you know what that is? And then we have oh dear. So this would be a typical kind of illustration of the sort of the framework that I want to model, and maybe a bit big. Shall I make myself smaller? And what are we going to have? So that is my illustration. So you can see that my illustration is showing me. My illustration is showing me a hinge, and it's also showing me this pivot on rollers. Let's put it on a surface. So when we come to draw our free body diagram, we're going to have those various joints, and we want to draw in R, we'll call that point A, RAX, okay, and RAY. So the hinge becomes these two reaction points. This weird thing here, where we've got a pivot sitting on roller coasters, that just becomes one reaction point. So if this was B, this would then be C. So we've got RCY. Okay. Where am I? Right, so that's it.